non-petroleum background. So, all right, I think we are recording now. I see a little cloud button with a little red dot pulsing, so that's a good sign. So, okay, so today we're gonna go over another one of our papers from URTeC. This is another one that's been very popular, generated lots of interest and lots of hits, and that is a GeoSHAP, which is what we call the sum of all of the Shapley values for the geology, which is essentially a total rock quality index that's derived via machine learning. And again, this one especially required lots and lots of work from various people at Novi at various kind of steps along the workflow. So truly a team effort on this particular project. And just like I did last week, I'm going to kind of give you guys a little extra context that'll help you kind of interpret the significance of the result separate from exactly what I say within the presentation, just because that's for a very targeted audience. So to set the table, why is it hard to know where the good rocks are? Question. So I pulled some data here from our WoodMac Midland model. Actually, none of this is actually model outputs, but this is input. So on the x-axis of this box and whisker plot, we have oil in place, and that is in units of million barrels per square miles. So it goes, from 0 to 130 million barrels per square mile. That's a lot of oil in place. And on the y-axis, we have the 2-year cumulative production of the wells. And you can see the median at 30 million barrels per section or per square mile is 173,000 barrels of oil production 2-year cum. At 130 million barrels per section, it's actually less than half that. Of course, there's lots of variation going on with completion designs and other things, but the main thing here is that oil in place in this instance is a very poor proxy for the rock quality and for what you should expect in terms of production. And this is the type of thing that if our model showed a Shapley value that oil in place is bad, we'd get kicked out of the room. Or if I were a geologist reviewing this with my boss, they would say, make a better oil in place map. Just because it's something that oil in place in particular is something that operators, investors love to anchor on. I will also note that this right here is one of the strongest signals I've ever seen for a single variable, single geologic parameter with respect to production. And yet it is literally going the wrong direction. Kieran is laughing because he knows. He's done these over and over again, and they never look this clean.
Yeah.
So if oil in place is bad, or it's a bad measure of rock quality, or sometimes it messes up, generally, what makes a good rock? So, or putting that another way, where are the sweet spots? What makes a rock high quality? Where should I drill? Question mark, question mark, question mark, question mark. So the first component of this, and for this, I'm mostly talking about rock quality for unconventional or shale reservoirs. But the first thing that you need is storage, quote unquote, which is the rock has some pore space. It's not just solid, perfectly solid. And that pore space has some oil in it. Very simple. Second is what people like to call deliverability, which is the rock has enough permeability to flow the hydrocarbons, and it has enough pressure to get those hydrocarbons to the surface in large volumes. The third, and this is most important for shale reservoirs, is frackability, and that is or how well the well will hydraulically fracture, and that is how much can you improve, number two, the deliverability of the rock by artificially enhancing the permeability and in small, maybe possibly pressure, but mostly permeability via hydraulic fracturing. So how brittle is the rock is how well it will respond to the hydraulic fracturing treatment, which by then filling with all those fractures, it becomes more permeable and will flow oil more readily. And we covered that in more detail in the last one of these. And so what are some examples of data types that would meet these three categories of what makes a good rock? For storage, you have porosity, you have oil in place, or hydrocarbon pore volume, or oil saturation, and then you have like net to gross style measurements, which are essentially like out of that rock column, how much of that is reservoir and how much of it is non-reservoir. So you may have a bunch of nice source rock with lots of pores and mature hydrocarbon and all that type of stuff. And there might be some blocks of like landslides and debris flows of other rock material that are kind of interbedded within it that are lower quality rock. Okay, for deliverability, that's things like permeability, which is literally how well fluids flow through the rock. You have the hydrocarbon type, which is pretty important. And the basic idea here is, you might have gas, you might have light oil, you might have heavy oil. Heavy oil is more viscous and it's not going to flow very well, especially through tight, unconventional reservoirs. And then the third, and this is very important, is pore pressure gradient, which is just what's the pressure of the rock, where it is, and really the pressure of the fluids, so the pore space. And then you just divide that by the depth that they are at to get essentially the pore pressure gradient. And then number 3 is for frackability, you have brittleness. Clay volume is a good proxy for that. You have stress regime, which is what's kind of the natural stress of the rock. That'll change how the hydraulic fracturing treatment impacts the stress or impacts the fracturing. And then you also have frac barriers where, like, if you're fracturing into some soft rock and there is like something which is really hard above you, your fractures may only propagate to the edge of the soft rock and they might stop when they hit the hard rock. Relatively simple concept. So in purple, I've annotated things that geologists and petrophysicists and geochemists love to argue about. Yesterday I lost an hour of my life during a conversation about oil in place and relative permeability.
The astrologers are good this, I've been told.
Yeah, that's right. Yeah, I was like petrophysicists are the astrologers of the subsurface. They're just like trying to figure out some way to get things like oil in place that, within a given basin might not be that instructive, to just like trying to get that somehow to relate to production by applying ever fancier ways of measuring it, esoteric stuff. So anyways, so there's lots and lots of time spent by those disciplines analyzing those different variables. I've annotated in red the pore pressure gradient. And I have to say, for anyone who objectively looks across this suite of parameters, either on a basin scale or across basins, the pressure is almost certainly the most important single variable. And the only reason that it's not considered more by the geologists who are, say, telling you where to drill is that it's hard to measure, first, and second, that the reservoir engineers are the ones who handle the data type. And honestly, I think that a big reason why geologists don't consider pore pressure that as much in their own analyses is because they just don't handle the data and the reservoir engineers handle it, and then they just like don't like to integrate it.
Well, in some ways it's easy to measure though, because that's just like the drilling med weight, right?
Yeah, but that's a proxy for it. Yeah. So I have a note on that coming up here later, but the reason that things like mud weight or in a conventional reservoir, you can use mud weight, or you can even use they actually will put there's a little measurement tool that they'll drop down the hole and they put on the side of the rock that can kind of measure the permeability or measure the pressure. The issue is that in tight shale reservoirs, it's so impermeable that the fluids don't the kind of true pressure of the rock doesn't express on the well bore because the rock is so tight. That's the basic reason why it's so hard to measure within shale reservoirs. It's not super difficult to measure in a very permeable conventional reservoir, like in the deep water Gulf of Mexico or in the Middle East. I will say that brittleness and especially clay volume is very important. Not really that hard to measure, and also very discounted. Kieran will know how many times we'll have V clay or some form of brittleness high on a SHAP NATO, and they'll be like, huh. And just for whatever reason, it's just frackability isn't talked about that much. Okay, so now we know a little bit about what influences rock quality. Next is how do we actually measure that? And so here I've highlighted the 3 main data types that relate to the actual rock properties. First, you have well logs. The advantage of well logs. So a well log, for anyone who's not familiar with it, is literally you drill a hole, then you take what's called it's called a wireline well log is what a lot of these are called, where you get essentially a cable that it's made of steel and it has like a data cable on the inside. And at the bottom of that, you have things like Geiger counters and resistivity measurers and things that shoot neutrons into the rock and various ways of measuring the quality of the rock and the properties of the rock. And so those are literally hanging by that wire, and they just run that down the hole, and that stuff just measures the rock properties as it goes. So the advantage of those is that they're relatively cheap. Some well log measurements are more expensive than others, and that, we don't need to go into that today, but at some point we may want to discuss that.
Yeah.
But
fun fact is also basically the exact same tools on the Mars rovers.
Oh yeah, that's cool. Yeah, but the Mars rover has like tiny versions of them that they can actually fly into space.
Yeah,
that's cool. So for a well log, the way that it works is essentially you can have many discrete samples around the basin. So hypothetically, you could run one of these every time you drill a well. Realistically, you might have, for things like neutron density sonic measurements, you might have one every square mile or one every 10 square miles, something like on that range, kind of depending on which play you're in. But that's an example of like how discrete the subsurface sampling is. However, well logs are only a proxy of the true rock properties. So there's petrophysics is essentially trying to take these raw well log measurements and relate them into physical qualities. So for core data, this is where you drill, when you're drilling your well, you literally like take a sample of the rock, and it's like a continuous sample. It's like these are 3 inches wide here, but you take like a tube of rock from the subsurface, bring it up to the subsurface. So the advantage of that is that you can directly measure the rock quality. So you can measure the oil in place, you can measure the permeability, etc. The disadvantage is that it's very expensive to do that compared to running a well log. You have to have a specific drill bit, and it takes a lot of time to actually get that core data out. And then all these measurements are also expensive, but the main expense is actually getting the core. So for the well logs, you might have those sampled every square mile to 10 square miles. The core data, that might be every 10 square miles to every 50 square miles, something like that, to give you a rough idea. And that's also going to vary by basin. And then seismic data, that's where they basically, it's kind of like, what's that thing when they measure for a pregnant woman, they measure the baby.
Sonogram.
A sonogram. It's kind of like a sonogram, but for the earth. So they have these trucks that sit on the surface, and they literally like vibrate they're called vibro-sized trucks, and they will vibrate really big, strong vibrations. And then you have separate, like essentially microphones that you've stuck into the ground that listen to those reflections of those vibrations off of the subsurface. And the advantage of that is that you can get a continuous 3-dimensional picture of kind of what the structure of the rock looks like in the subsurface. It's expensive, so that's bad. And the other thing is it's seismic. If you want to relate it to rock quality rather than just rock structure, that you have to in some way calibrate it to core data and well logs to take some of the attributes of that seismic data and kind of use them to get a continuous measure of rock quality.
Hey, Ted, so clearly the prohibiting factor here is the expense. Yeah. What does the decision-making process look like when people decide to go after core data or seismic? So clearly they're not going to do it every square mile, like you said, but yeah. When do they decide to go after core data or seismic?
Yeah, so that's going to depend a little bit on on 2 things. Number one, what the pre-existing set of data availability is within that play. So if you're working in the Permian Basin, it's the most data-rich basin on the planet, just because it's been drilled. I mean, there's 200,000 wells that have been drilled in the Permian Basin. So it's extremely data-rich. In that instance, you might only get core data if, let's say you are ExxonMobil and you have 200,000 acres in southern New Mexico that is a continuous chunk of a block, and you really want to get to the nitty-gritty on where you're landing your wells and how you're fracking your wells and your physical modeling and your 3D geocellular models and all of that, you might take some core samples. You might drill some wells, take some core samples, do some very complicated, expensive well logging. They might be spending $15 or $20 million on one of those wells to get that data, because it will basically be used to calibrate many of their future efforts. And for 200,000 acres, Exxon in the Permian is probably going to end up spending $20 or $30 billion developing that. So that's why $10 million, or even if they do a suite of those, $100 million to help protect that $20 billion investment for them is a good call. Okay, so now I want to have a special note on pressure data, just because I called it out as being like the most important and the hardest to measure. Kieran already basically asked the question about mud weight. So the idea for mud weight is, you drill the hole. You have what's called, the drilling fluid is the mud, and because it looks like mud, and it's essentially it's water or a diesel-based fluid that they add things like bentonite clay. They might add some lubricants into it, but the idea for the mud is that it cleans the wellbore. Is one of the functionalities. The second functionality is that you don't want raw rock just exposed in a hole, because that rock, if you're 10,000 feet down there, that rock has 10,000 feet of rock on top of it, and if you expose that to air, which is at 1 atmosphere of pressure, that rock is just going to shatter into the wellbore, and you're going to lose your well entirely. So in order to keep the well from shattering in on of itself, they put essentially heavy mud that's very dense. So that's why they put bentonite. They'll put barium sulfate in it. That's very dense material they can add to the mud. So that will essentially hold back the rock. So here on this little chart, this orange line, and we have depth on the y-axis, and we have the mud weight, which is in pounds per gallon on the x-axis. That orange line is the fracture gradient. And that's essentially like how heavy the mud has to be to, rather than hold back the rock. Eventually, if the mud is heavy enough, it will start breaking the rock on its own basis. So basically, you want to keep the rock from breaking in on you, and you want to keep from breaking out on the rock. And the pore pressure, or the pressure of the fluids inside of the rock, if you're drilling and you consistently reach a zone, let's say the Wolfcamp A, and all of a sudden you have to increase your mud weight to keep from hydrocarbons and stuff flowing in the reservoir, that's a good indication that it's very highly pressured. Now, the caveat applies in low permeability shale rocks that it is very rare. It's even if that stuff is extremely highly pressured, it may not be flowing into the wellbore just because it's so tight. But that can still be a good proxy in some instances. Another piece of data that you can use to kind of measure or guesstimate what the rock pressure is, the pore pressure, is called a DFIT, and that's a formation integrity test. I forget what the D stands for. And that's basically where they will, they'll pump some water and some fluid down there and try and break open the rock. And so it's just, they can infer, they can infer based on the curve of the pressure of the fluid that they're shooting into there, kind of what the pressure of the rock is. So a third measurement of the pressure is sonic well logs. And these are literally, it's how fast do sonic waves travel through the rock. So they'll have like on the tool that they drop down the hole, there will be like essentially a sound source. And then, 10 meters above it, there will be a microphone, and they'll attach both of those to the rock. They'll shoot a sound source and measure how long it takes for that to get up to the microphone. And that's a good measure of it's an indirect measure, but it's a measure of the pore pressure, because essentially if the rock if all the fluids in the pores are pressing open on the rock from within, stuff will travel very slowly through that, compared to if the rock is allowed to kind of stay solidified. So we do have sonic well logs. That's the good news. That is a common well log to have. So that's actually probably the best measurement you can have for pressure in terms of the stuff that we deal with. Okay, so now that I've laid out all those data types, what did y'all just do? with their daily lives, other than geosteer wells and spend days drawing well sticks. First is stratigraphic interpretation. So what I have here, these are 6 wells, and there is a well log, like for each of those, there is a well log, and that's like that little squiggly line is, that's like a gamma ray well log essentially. And when a geologist does stratigraphic interpretation, they are just trying to build a geologic framework or context for all of those well logs to pick some surfaces through them that represent consistent time surfaces or consistent boundaries between rock types. So we don't need to go into too many details, but this is like a lot of what geologists do is this type of interpretation where they build these very fancy charts and have all these picks or tops within the rock or within the well logs. So once that's built, then they do some kind of data integration where they use the stratigraphic framework that they built in step 1 to put the well logs, core, seismic data, pressure measurements, geochemistry, and production data into some kind of a context to say like, okay, yes, I think this is what is driving production. I think we should drill our wells here, et cetera. Get some idea of that. And then a third item that they do is they will make maps that kind of represent those learnings from the data integration. Things like, okay, what is the gas in place? So that when they go to lease or when they go to prioritize their own drilling inventory, they know kind of where the best rock is. Okay, so that is all, 20 minutes of context for you guys there about kind of general subsurface approaches and thoughts. And so now kind of switching gears here, the workflow that we're presenting today starts from raw well logs that we then run through a principal component analysis that we put those principal components into our model, and eventually out the end pops GeoSHAP, or essentially the machine learning rock quality index. So for us and for some of the questions that motivated this workflow or ways that we use to sell or message this particular workflow, number one, what makes a good rock? And you saw from the very first, honestly, very rare to actually see a single rock quality index map. People might say, here's my oil in place map, or here's a map of gridded production, but a single rock quality index is a rare thing to have. Second, and this is a question that we will pose sometimes, or sometimes people will pose to us, but that is, can you estimate rock quality, or can you build a machine learning model straight from the cheapest and most widely available data, which is logs? You save time and money, you simplify the process, and you take geologists out of the process, which is engineers love to do. And John and I had a conversation with a couple engineers yesterday who were basically bragging about how they had done that for some of their own internal workflows. And then number 3 is, how do you handle the sheer volume of collinear subsurface data? And this is kind of a lot of what I proposed this particular talk around, but just for a little more context on that. In the course of working on Data Engine, we decided it'd be helpful to have a list of the possible geologic properties that someone might provide to us. So I made a swing at just stuff that I could come up with, and if anybody wants to look at this tape, you're welcome to. But I came up with 70 properties that I thought reasonably someone could give to us. There are many more, and a lot of times there are derivations of these that you could make. You could have the P95 for the gamma ray, or you could have the standard deviation of the gamma ray as examples. And so for Pioneer gave us, what was it, 300 plus grids that they extract, or not grids, but 300 plus geology values that they had extracted to their well bores. So the number of possible geologic properties, that feature space is almost endless. Okay, so now I'll actually go into the talk. Now you guys know some stuff. So motivation for this talk, I've already covered kind of the issues with the data sets, but the other thing kind of generally that the industry struggles with for machine learning is a lack of interpretability. And having a tangible rock quality index that the machine says, yes, here is where the good rock is a very nice tangible thing for management, engineers, whoever, to latch onto as proof that the model has understood the rock. The other reason why this principal component analysis workflow is useful, especially for geology variables, is that functionally, because of the nature of publicly available data and the fact that we are almost always working with some hybrid model that incorporates publicly available data, we are functionally limited in the number of completions variables we could use, because there's usually only proppant volume, fluid volume, stage length maybe, and maybe proppant and fluid types are available in the public domain. So you only have maybe 5 completions variables that you can work with most of the time when we're building models. But in terms of geology, that's usually operator provided, and it's something that is nearly unlimited. Further to that is that geologic variables are often highly correlated. So the deep part of the basin will have higher maturity, higher pressure, higher hydrocarbon in place, higher hydrocarbon pore volume, higher P95 hydrocarbon pore volume. It might have its own geologic facies, because what is deep now might have been deep at the original time of deposition. So this stuff can be very highly correlated. So that may mean that some variable that is the pet variable of some geologist on the project or of a manager, that might get dropped. And so now the subject matter expert is like, well, model drop permeability, why the hell would I listen to that? I mean, how many times have we heard some version of that out with the customers? It also just might be that the model picks depth as its most important feature, depth, which is highly correlated with pressure. And then something down at the bottom, like whatever their permeability height map that they spent days working on is at the bottom. So that causes trouble for us. Okay, so the workflow that we're presenting here, it starts from raw logs and tops. We already had some formation tops for this one. And then some geochemical data that was publicly available. We then run that through a zone classifier and a property summarizer that produces a set of geology variables. And this is all stuff, Kieran did all this. Then we run it through a principal component analysis to get a set of PCA features. And I think Chris and Kieran were working on that for this project. Rami, were you on that? I forget, but.
Probably.
Yeah. Data scientists did that. So then we take those principal component analysis features, run those through the model as the only geologic features, and then we get SHAP values for all of those. And then if we sum all those up, we get a GeoSHAP. So that's the basic workflow. And so in this talk, I'll kind of step through that workflow and the various kind of products and components for it. And this is very, very popular with the customers. But so here is a Novi Bakken model. We're working with data from the NDIC, the North Dakota Industrial Commission. Kieran built a classification algorithm to pick lower, middle, and upper Bakken tops using neutron or gamma ray logs. And this is maybe the clearest instance in all of lower 48 of it's like maybe the easiest top to pick, just because the gamma ray values and the neutron porosity values for the upper and lower Bakken shales are so freaking high that it's very easy for a machine to pick. So it's not something that you need a sophisticated geologist, experienced geologist to pick. We had depths for other formations in the column, but we used this to make picks for those Bakken intervals. And so then we use those tops that were picked by the algorithm to extract zonal statistics or kind of various statistical properties of gamma ray, resistivity, sonic, neutron porosity, bulk density, and spontaneous potential logs. We also had some mud log gas measurements, and those are when they are drilling a well, there's the mud gas, which we've already talked about, or there's the mud, drilling mud. When that stuff comes up to the surface, if it's in a hydrocarbon bearing formation, it will be bringing up some small amounts of gas with it. And you can measure the chemistry of that gas to get an idea of some of the properties of the fluid that's in the reservoir. Essentially, if the gas has C2, C3, C4, rather than just C1, rather than just methane, that's a good indication that you have oil. Okay, so then we ran the, it might have been over 300 features, Kieran. Do you remember what it was being?
400 something.
400 something? All right, cool. There's a lot of features.
Not
So
important.
we reduced those down to 5 using a kernel principal component analysis. Any, is Chris on the line, or Rami, or any of you guys want to explain this process to other people?
Yeah, I'm on the line. For those of you familiar with kernel or familiar with regular PCA, the notion is that you can take a data set and decompose it into a linear combination of transform variables for that data set. The kernel part of this allows us to take advantage of nonlinear relationships. So we tossed out this idea of using a kernel PCA as opposed to a linear PCA because we know that many of the geology variables are related, but they have nonlinear relationships. They have differences in the extremes of those data points. They have differences in the range, and in general, just the functional relationship is totally wild, going from one to the next. But we know generally, like, big numbers correlate to big numbers, small numbers correlate to small numbers, etc. So what the kernel PCA allows us to do is to then sort of differentiate whether lots of big numbers exist for all those variables, lots of small numbers exist for those variables, or lots of middle space numbers exist for those variables. As a cartoon, it's like looking at these concentric circles, and the PCA version of this, you would not be able to linearly separate the green from the red from the black. But with kernel PCA, you can say the black is very close to the center, the red is somewhere in between, and the green is pretty far apart, assuming you're not colorblind. And so that's what we did with the geo features.
Great. Thank you, Chris. That is better than I would have done. So here are the 5 principal components, as well as the top input features that went into each of them. And I find this very interesting because the model is able to pick on stuff that I know are real geologic features without any kind of forced input. So for instance, GeoPCA 0, you see the oranges and the cream colors around the edges of the basin, and the blue is in the deepest parts of the basin. So, hey, look, it's identifying the basic basin geometry and structure. That's nice. GeoPCA 1, you see that has a lot of sonic measurements in that, and it's very high, or actually that's probably low, but very low over there in the eastern part of the basin, and along our little piece of the red there along the Nesson anticline. And I know that from my previous work in the basin that those are highly overpressured parts of the basin, and they're also extremely high producing areas of the basin. So it's cool that the model is able to pick that up. PCA 2, that one is somewhat cryptic to me. Same with PCA 4, but PCA 3 that picks up the Nesson anticline, which is a large kind of arch that goes through the middle of the basin that has a lot of oil in it. Okay, so for input variables, we had proppant and fluid volumes and stage counts. Those are what's publicly available within the Williston. We did our standard spacing calculations, timing, etc. For the geology, it was just GeoPCA 0 through 4. And then I want to emphasize here that we did not include the operator categorical, nor do we include latitude, longitude, county, or area, which are, so essentially the model has nothing which is explicitly geographic. Operator can tend, because operators usually have concentrated positions that can often represent a specific area of the basin. So pretty cool that the model is able to learn where the high rock quality is without essentially being told even where the wells relate to each other in physical space. So here we have the SHAP NATO at 720 days. You can see that the proppant and fluid rank is most important. And then you get into a lot of the GeoPCA features. So of course, geology is very important, even if geologists are wrong a lot of times. And it's nice to see that the model has those ranked very highly, because that's for a basin-wide model that needs to be the case. Okay, so here I have the GeoPCA features along with the Shapley values for each of those. And so if it has, you can see there's 0, it kind of moves up and down on each of these features. But you can kind of see that, okay, the model's like, if you're in this really shallow stuff around the edge of the basin, you should be punished for that. For this GeoPCA one, it's like, yeah, you're in really good business if you're over here at this for these high values, which, as we mentioned, are in those overpressured parts of the basin. GeoPCA, 2 and 3, you can see it's picking up the Ness and anticline, saying there's good production there. Still not sure exactly what's going on with that one. And GeoPCA 4, I mean, those are some kind of hot spots. This one is actually, there is a hot spot right there in the basin for some reason that I don't fully understand, but GeoPCA 4 is able to kind of pick up on that. So that's kind of neat. The other neat thing about this is that, the shapes of these SHAP value curves are different for each of those. So it's interesting. It's like for the GeoPCA 0, it's like for that particular variable, it doesn't really care whether you're, 0 to minus 0.5, which I just thought was interesting. Okay, so going from those individual principal component SHAP values to a GeoSHAP, where we roll it all up. And I believe, was it Mark Millett from Birch who originally termed this? So it's very simple. We just in Spotfire or Pandas or wherever, we just sum up the Shapley values for all of those and then give it a nice color bar, and you have a map of the rock quality around the basin. And let me go ahead and flip over and annotate. The model has picked up what I know to be the 3 best producing areas of the basin, the Ness and anticline right there, the Fort Berthold area right there, and then the partial Sanish field over there in the northeast. And the other interesting thing that's going on here, I didn't get into too much detail of this during the talk, but really each of these 3 is a really hot spot in the basin for different reasons. The Ness and anticline, oil has migrated into the arch. And it's a structural trap is what we call it. The Fort Berthold area just has extremely rich source rock. So it's very high in TOC, et cetera. And then the partial Sanish is a stratigraphic maturity trap on the edge of the basin. So it's also a migrated trap, but the trapping mechanism and depth is very different than the Ness and anticline. So to me, it's extremely interesting that the model has picked up on that. And qualitatively, I mean, we've reviewed this with people and people nod and say, yes, that looks good. Actually, I think almost every time we've shown a GeoSHAP map, no matter what the basin, people are kind of like, it looks correct. So the other cool thing about this, and we may cover this in another talk because it was another URTeC presentation, but one thing that we do with it is we'll take that GeoSHAP value and just cross-plot that with the actual oil production of each of the operators. So you see there's a nice, relatively linear trend between the two. And this vertical bar right here is a company called EOG, which if you know anything about the oil industry, you know that they are the best of the best. They're thought to be by far the best performing company. And some of these other ones that are up here are kind of ahead of the pack, who are also producing more oil than their rock quality would predict on just on its own basis, are small operators and have very few wells. EOG is the only one of the big operators who has really any differentiation with respect to its peers in a similar rock quality. So I think this chart is what convinced Ian Yingling from Black Swan to side Novi. So we will also use the GeoSHAP in conjunction with our other kind of SHAP plots to provide some context for them. So a very common question that people will come to Novi with is like, should we be customizing our completions or our spacing or our X to specific rock qualities? And GeoSHAP is a good summary of the overall rock quality. And as such, it can, help you kind of figure out, like, if you're an operator who has some rock here in the good stuff and also some rock over here in the poor stuff, like continental resources, should you be applying the same completion design in each of those? And of course, the proper way to do it is to actually run those designs through a forecast engine. But when you're doing your kind of research and development, you know, just doing some exploration insight style stuff, the GeoSHAP can be very useful in binning that data. So we also, we used it for kind of GeoSHAP is very useful for kind of like basin style studies. So in this particular one that I'm showing you an excerpt from here, I have a play map of Bakken over there on the right, and I've blanked out everywhere where a well has been drilled, and with a 600-foot buffer on either side. And you can see there's a lot of stuff missing where there should be some green. And of all the wells that have been drilled so far, you see this is just a histogram of those across different bins of GeoSHAP. Not very many of them have been drilled in tier 3 acreage. Maybe 40 to 50% have been drilled in tier 2 acreage. And then some, you know, 30, 40% has been drilled in that tier 1 acreage. However, if you look at the remaining inventory, really less than 9% is in tier 1 acreage. And of that stuff that is in tier 1 acreage, I did a cursory look around Google Maps and everything. And just from my own experience, I know that a lot of this stuff that hasn't been drilled is because it's under a gigantic lake or in extremely rugged terrain or a national forest or a national park. So that's why a lot of these big green chunks are kind of still left on the map, is because it is logistically quite challenging for some reason or another to drill there. So if you're the state of North Dakota and you're thinking about your revenue expectations for production taxes, something like this should be very concerning. Before I show you the conclusions, I just wanted to do a couple fun, quick hits of other. I just Googled like Bakken rock quality or Bakken oil in place. Here is a map from Hard Energy, which is a publication that focuses on the oil industry, where they have just gridded. They just have a map of all the EURs around the basin, and you can see that. Yeah, I mean, maybe if you applied some kind of smoothing stuff, you could get something that shows you the relative rock quality. But it's making a decision on this type of a map versus on like that. You can see that it's much clearer trend that you get with the GeoSHAP than you do with just mapping how well the wells have produced.
It says that total EUR helps identify spatial patterns.
Yeah, exactly. Yeah, I mean that's yeah. This one was also fun. So this was an RS Energy blog post that they posted in June, a couple months after ours, about the Bakken. And so in this they go, okay, the recent collapse in oil prices, dramatic drop in activity, et cetera, et cetera. As prices recover, we expect to see high grading will return to areas with the highest quality rock. Okay, on board. In the Bakken, we view the Fort Berthold Inland Reservation as an anticline Little Knife as the core of the play. Yep, we're all in agreement. So let's look at their map of those core areas of the play. This weird rectangle, that is one of their core areas, and this Fort Berthold Indian Reservation is the other core. So they just say like these two half counties are core, and they just call it that. And so the resolution that you can get using GeoSHAP for something like this compared to like, this is so gross. I mean, it's such a gross generalization of what's going on with the geology. I'm almost amazed that they even put this thing out. Also, fun tidbit, as I was Googling Bakken rock quality, I went to Google Images, and hey, check that out. We're number 4, baby. Here we go. All right, we're coming for number 1. Okay, so now some conclusions. So this workflow that we've presented provides a powerful method to estimate rock quality from log extractions, principal component analysis, and SHAP values. Those are kind of the three key components of the workflow. We are able to use GeoSHAP to identify high producing areas without being fed any explicit geographic information or any interpreted geologic products. We just took the raw data, fed it through. useful in conjunction with other SHAP values for regional studies, many different things. We also, even though in this paper we presented a workflow that started with the principal component analysis features or whatever, we use GeoSHAP no matter what the input features are. I mean, you can use it for interpreted products, anything. So this style of a workflow is quite generalizable, using each of the components to do kind of individual things. So that's about it as far as the presentation. What kind of questions do y'all have?
So Ted, this is great. I do have a couple of questions for you about the GeoPCA.
Mm-hmm.
So you're looking at Shapley on these derived features, and then you show what are the top features going into, say, PCA 0.
Yeah.
If you compare that to some of our normal models, you get Shapley on the actual data, the actual features going in. In your view, is there more work to do to be able to say more than just here's the SHAP on GeoPCA 0? Does it, for this kind of model, should we be able to say here's the SHAP value on porosity specifically?
Yeah. So certainly there's some utility in being able to do that type of work and be able to show that type of feature specific Shapley value. I do think that most people just kind of accept this. I mean, Kieran's nodding, but it's for whatever reason, and this is actually, I didn't get into this during the URTeC presentation, but this gives just like a little magic dusting of machine learning over the whole subsurface process that it does like jujitsu on people who are blockers on our subsurface data. The real advantages of this is, go ahead, Kieran.
Yeah, it's like magic. Like these people could sit around and argue about, if you go back to Ted's first slides, the astrology of the subsurface stuff, they could spend hours arguing about this stuff, but then you just show a GeoSHAP map and it looks like what it's supposed to look like and everyone's good.
Exactly. And you can also basically say like, oh yeah, your permeability, yeah, that one went into GeoPCA too. Look, here's where it says the high producing areas. They're like, cool. I mean, we haven't done that exact exercise, but it feels like that's the advantage, is to kind of, you can actually incorporate all those interpretations, literally it's in there.
As we go to productize this, do you mind going back? I think it's like 3 slides, maybe. This one right here, 14. Like giving this information right now, you're able to do it with PowerPoint easy. You're probably able to do it with an Excel spreadsheet easily, but getting this right might be, I'm not sure exactly how we're doing it today, but making this generalizable to where we just say, okay, there's GeoPCA 0 in the model, but what is represented by GeoPCA 0, I'm assuming it's pretty manual today. That would be something we'd really need to think through. But I mean, this is overall is very, very useful. We're gonna have to think it through how to deliver.
We're not actually delivering GeoPCA to any customers right now. Usually I will just sit down with them and say, a lot of what Ted just said, like these things are going to be collinear, they're going to vary together. Not all your favorite maps are going to make it in here. Some will make it in here and it'll look irrelevant or they'll go the wrong way. And that is something that I'm going to explain to you why it's going to happen. And then you need to think about what maps you really want in here and trim it down to like less than 10, because you're not going to have both an overpressure map and a depth and a permeability and a porosity map all looking as important as you think they are, because they're going to vary together.
I mean, but as we go into model engine, I hope you'll agree that, if we're going to do geo-specific kernel PCA, that we're going to turn that over to the user. So in essence, we're going to be annotating those geo features. And then if we decide to do kernel PCA in general, like as like the Novi secret sauce, that's got to be done in some automatic way. And you're going to have to reveal this kind of insight to the user, or potentially, as we really scratch the surface on this, maybe additional insight. That was the motivation of my original question.
Yeah, that makes sense to me. And I do think it's worth thinking about this stuff as we go to subsurface 2.0 or go to model engine and start enabling these type of workflows. Yeah, I think it is reasonable to want to output what went into the principal components. The other nice thing about this is, if you remember, I went all the way back to, I was like, okay, here are the 3 things that matter to the rock, right? And, you know, if I look at these set of principal components, this doesn't map one-to-one to what I laid out, but I go, okay, 0, that's based on architecture, check. 1, that's overpressure, check. 2, that's source rock maturity, check. 3, that's migration, check, or, you know, et cetera. So it's just, I can look at these and I know kind of what roughly they represent in abstract geologic terms.
So Ted, that's interesting, because like I told you, like we're kind of just scratching the surface, in my opinion, on this. Like as we get further along with this, I think what would be useful is to start saying, attaching metadata to these measurements. Like as an example, you classified, you know, say something as frackability. So which of the measurements out there are frackability? There, I think there's a lot of additional work we could start to do to tie these 2 things together, as opposed to just like, here are the raw measurements and you figure it out, user.
Yeah,
I think
exactly.
This is
be
awesome.
done. Yeah, we also, you know, in the Bakken, frackability really doesn't matter that much because the geomechanics of the reservoirs varies little across the basin. Whereas if you're in the Eagle Ford or in the Permian, you do have very large differences in clay volume depending on where you are in the basin, just because of the way stuff was geologically when the rocks were being deposited. So
yeah, so I mean, like what would be interesting to me is like, you know, you have a frackability map, right? You see what I'm saying?
Yeah, exactly.
So well, you could come up with SHAP values which are associated with grids, which are associated with frackability.
Yeah, but the thing is like you're not able to right now disentangle these PCA features, especially because of the kernel part of the PCA, into those individual measurements. So I think summing those into frackability would be a little hand wavy and a little bit challenging. In essence, what I'm arguing for is like if you're able to disentangle the Shapley values into the individual measurements. So instead of GeoPCA, you're able to do it in terms of Cedar Lake formation depth, which may be corresponding to one of those 3 measurements. And then you're able to sum across that and potentially you have, here's my frackability map. Or what were the other 2? I just keep saying frackability test.
Storage and deliverability.
Yeah, so here's the deliverability map. What are the features that go into deliverability, right? But we would have to disentangle that kernel SHAP GeoPCA. I don't know. It's just something to really think about as we move forward.
Yeah. Now I will say one of the advantages of it is that it does lump everything together. Thus, there's nothing counterintuitive for any of the input features. So, I mean, there's a balance to strike between, and I don't know where it is, and this is something for us to think about. We should also be thinking about this is we're going to have the opportunity to build a lower 48 wide model with the WoodMac URTeC that, you know, I don't know, we've talked about this too much, but shortly on our list to do at some point this fall is to build a multi-basin model from 8 basins, Kieran?
It's 5.
7? 5, whatever. 5 basins. 5 basins, and maybe we'll get to some more later, but 5 basins worth of lower 48 data that has interpreted maps that have things like these measurements in them. So maybe that's something we might want to apply a principal component against that. I don't know. The interesting thing is going to be how this changes in a multi-basin environment. I think that's going to be really interesting to see, because right now, and this is something that I just kind of wonder generally, is how much of this is just the model is using those input. You know, when I see this stuff makes sense to me in terms of rock properties, but to some degree, it might just be using them to kind of learn what areas of the basin are, you know, where rocks are in the basin. So, you know, if we go to a multi-basin model where you can't just learn that type of stuff, and you have to, the multi-basin model will have to some degree, I would think, has to make physical sense. Yeah. So we'll see how that goes. It's an open question mark for me.
Cool. Thank you for answering my questions.
Any other questions?
Cool.
All right. So we will continue. I think our next lunch and learn, Dylan is presenting on free lunch. So thank you, Dylan. But we will continue to do topical lunch and learns. If anyone on the front end or back end team has something they would want to present, I think it'd be great to hear something like that. We have 6 more of these or whatever from URTeC to go through at some point, but I'd love to have a diversity of highlights throughout the company. So I'm not going to volunteer anyone yet publicly, but maybe next time I will. Okay, everyone have a good afternoon.
Thanks, Ted.
Awesome, Ted.